Dr. UlHaq, who's recently completed his PhD dissertation from the University of Stuttgart. Dr. UlHaq completed his bachelor's in engineering science from the GIK in Novi in 2003. After that, he joined the University of Stuttgart, where he completed a master's in physics. He also worked at the Max Planck Institute for Solid State Research in the same city, and later he spent some time at Hamburg University as a research scholar working on plasmonics, that is surface plasmons and metal materials. He then worked as a research associate for a year at GIK. In 2008, he won the International Max Planck Research Scholarship and he worked towards a PhD at the University of Stuttgart, working on coherent and cascaded photon sources using semiconductor quantum dots. So, without further ado, I would like to welcome Dr. UlHaq.
Yeah. Thanks for the nice introduction. Today I would like to talk about the work I did during my graduate studies at University of Stuttgart. So the topic you can see there is address state emission from single quantum dots. So most of the work which was it was done at University of Stuttgart at the Institute of Halbleiter Optics and Functionelle Grenzflächen. For those of you who don't understand German, of course there's an English translation. Yeah, so it's kind of semiconductor optics and functional interfaces. Yeah, so as an outline, so what I would talk about is resonance fluorescence on single quantum dots, and I would mainly focus on three aspects of resonance fluorescence from single quantum dots. First, I would talk about the photon statistical character of the photons which are emitted in a resonance fluorescence from a single quantum dot, and the second part I would talk about dephasing, which we study in the resonance fluorescence emission from these structures, and finally like using dephasing mechanism as not as a bad tool, so to say, but use it for real application in a new phenomenon called as non-resonant quantum dot cavity coupling. So to start, I would just start with semiconductor, just an introduction of semiconductor quantum dots. What are they and what are their properties? So, and why do we need them? So, to give you a brief overview of why we want to do this work is basically quantum photons are like quantum entities which one can encode information as a qubits and which one can transport from one place to another, like in quantum communication. And one can use, for example, polarization state of single quantum dots to store information, just like in different configurations or a mixture of them. So there are different proposals to use such single photons for quantum communication scheme, like this well-known BB84 protocol, where the indeterminacy of quantum states preparation is used to transmit securely information from one place to another while choosing different bases of polarizations. So this scheme, for example, it works on single quantum dot, but if one wants to do long scale communication of such photons, then one need a kind of a repeater system or kind of a quantum repeater which acts on the basis of quantum teleportation. So for this you need single photon, but for this you need highly coherent single photon so that they can interfere in a highly coherent way and thus make possible the quantum interference, which makes the principle of quantum teleportation. And so that's why we use single and cascaded photon sources which use these properties. So another application, for example, linear-based application of quantum computation, for example, the well-known scheme of Nilla, Flamel, and Milban, which is based on single photon sources and photon detector and linear optical elements, and a combination of all these three makes a full quantum computational circuits, and one can use even cascaded photon sources in such a case. So, but for this also not only single photons or cascaded photons are needed, but they are needed with high coherence. So coherence is a really important property in all these measurements. So as I said, so for quantum information processing, photon sources are needed, and those photon sources, they need to be highly coherent. And what do we mean by they need to be highly coherent? Is that they should exhibit kind of quantum interference effect, which is called as Hong-Mandel effect. So if two photons are incident on a beam splitter, the Hong-Mandel effect says that the transmission, that both are transmitted or both are reflected, the probability of this should be 0 if they are perfectly identical. If they are not identical, if they are perfectly identical, then this should be 0, and both the photons should be emitted on the same beam splitter in either case. So this is the so-called Hong-Mandel effect, and both these schemes which I showed earlier, they are based on this effect. So what are the systems which can be used to produce these photon sources? There are different sources available. For example, currently the most importantly used source is the parametric down conversion sources which are used. But today I would talk about systems which are based on single quantum emitters, and there are two broad classes of these systems. The most important one is so-called isolated system, which is made of isolated atoms, trapped ion and Rydberg atoms. So they are more or less very clean system and with much low dephasing. And another system are the solid state based system, which consists of, for example, NV centers in diamond, nanocrystal, and quantum dots. The problem with isolated system is they are really nice, they have high coherence, but the problem with this is they have issues with compatibility. So to integrate this system into real quantum circuits is a real big task, which is somehow difficult to tackle. The benefit of solid state system is even though there is dephasing in these systems, still the compatibility is much easier. So for example, I would talk today about a quantum dot system, and a quantum dot system which is kind of a solid state system which is made of a material which has low band gap and which is surrounded by a material which has higher band gap, and the confinement as such provide a single quantum emitter in this case. And such a system is favorable because it is a semiconductor based system, so it can be easily integrated with semiconductor technology which is existing and which is highly developed. Another important thing is they are there's really relatively good control over the properties of this. For example, you can't change the emission frequency of atoms, but you can tune the emission energies of quantum dot very easily while growth and also while post-growth processing techniques, and also the samples are compact and stable for a long time. So today I will talk about quantum dot. That's why we choose quantum dot as our system of choice for the measurement. So just a bit about semiconductor quantum dots, maybe if some of you are not aware of the system. So
I don't understand, how will you get two photons which are very much coherent using quantum dot or isolated atoms? You produce two photons, how would you make sure that they are coherent?
So there's so you can do Hong-Mandel kind of experiment on this. There are different kind of experiment by which you can measure coherence, of course.
Yeah.
You can, of course, use a Michelson kind of interferometry to measure the coherence. Another effect is directly to use a Hong-Mandel kind of experiment and interfere them at the beam splitter and see if they exit at the same, both of them exit at the same output port or not. And this would be a direct measure of the coherence.
How would you produce coherence?
This is what I would talk about now, like how can we achieve higher coherence in these systems. So this would come. Yeah. So one can think of a solid state, a single quantum dot as a three-dimensionally confined structure in which you have a small band gap material surrounded by a large band gap material, and electron hole pair which are trapped inside this material. They are somehow like trapped in a quantum well, and that's why a three-dimensional confinement provide kind of atomically discrete levels. The internal electronic structure of such a material consists of these different shells. For example, the single electronic shell and single hole shells, which can be occupied by electrons and holes. And depending on the spin of electron and holes, they can occupy different. They can have different configuration. For example, if we consider only the ground state here, the ground state have these 4 different configurations. For example, a neutral exciton state, to a charged state and a bi-exciton neutral state, which consists of a pair. And this filling of the state depends on, of course, on the Pauli principle. So what we are interested in is its neutral exciton state. So what we are interested in the transition of the neutral exciton. So the neutral exciton recombine and drops to the ground state. So you have an excited state which makes up the neutral exciton state and a ground state which consists of empty quantum dot. So if you look at the energy of such an exciton ground state, it is degenerate. It is characterized by the total spin of the electron plus holes, and if one takes into account the exchange interaction between electrons and hole, then it splits into a bright exciton and a dark exciton. And because the quantum dots are not circularly symmetric, and if one take the structural asymmetry of the structure, then the bright exciton further split into further components. So what you have is this bright and dark splitting, and further the bright splitting is further split into two components, which is called as fine structure splitting normally in literature. The dark state you cannot optically access normally because they are dipole forbidden. So going back to the question you asked, like why do we need highly indistinguishable photon, which means that all the photons which are emitted from the quantum system, they have the same pulse width, they have the same frequency, the same mode profile, and the same polarization, and only then they can undergo this Hongomandel kind of interference. So the question is, what about the quantum dot system? Can it provide it? But if you look at a quantum dot system is not an isolated system. It is a highly open system, such that it interacts with the phonon path surrounding it, and it interacts with the charge carrier, which are in the semiconductor material. So it also a lot of charge scattering in such a material or such in a solid state. So what happens because of these interactions is that the system, the quantum interference in the system is decoherent, and the photons which are emitted, they lose coherence.
I have a question.
Yes.
In the pulse width, are you talking about the wave packet, or are you talking about the pulse of the light?
No, I'm talking about the pulse of a single photon, the pulse width of a single photon, which is determined by the lifetime of the excitons of the excited state. Yes, so it is determined by the lifetime of the excited state. Yeah, and it is important because at the end they have to interfere at the beam splitter in a Hongomandel effect, and if they are different, then of course the effect would not be fully visible. Yeah. So just to quantify this whole dephasing thing, it can be quantified into a total dephasing rate, which is given by a T2 normally in a two-level system, which is given by a radiative dephasing and a pure dephasing, and a pure dephasing in a two-level system such as this is given by both the phonon scattering and carrier scattering. So the best one can do in this case is to just make the pure dephasing as small as possible, so that the effect of this pure dephasing is minimal, and the total dephasing is only given by the radiative dephasings, and this is called the Fourier limit normally in literature. So the goal in our case is to minimize this pure dephasing as much as possible.
So
Yes.
Can we have a T2 larger than T1? Or is this the limit? Generally T2s are much smaller than...
Yeah, there is one case under resonant excitation which is much below the saturation of the quantum emitter, in which you can have larger, but that is a very special case. Normally if you are moderate excitation power, this is the limit. That one can reach only under resonant excitation at very low power, much below the saturation of the emitter. So that's another regime. I won't go into the detail there. So one strategy I would talk, normally one applies is to embed these quantum dots into optical microcavities, and this is what happens in this case is in the weak coupling regime, where the coupling strength is smaller than the losses in the cavity, the Purcell factor counts, which quantifies the increase in the emission rate of the quantum emitter. So the quantum emitter radiative lifetime increases as shown here. So if you have a quantum emitter which is out of resonance with a cavity, then it has a larger lifetime. The moment it goes into resonance spectrally with the cavity, the lifetime drops drastically. And the ratio gives you the Purcell factor, the experimentally measured Purcell factor. So what happens in this case, if the radiative decay is faster, what happens is the pure dephasing processes, they don't change in the presence of cavity. And if the radiative decay is faster, the role of pure dephasing processes become smaller and smaller. So the faster you run the system, the smaller the pure dephasing, the effect of pure dephasing is. Another approach to do is to change the excitation mechanism, which normally applies. So the normally,
What do you mean by radiative?
like by what?
What is radiative dephasing?
Radiative dephasing is the dephasing caused by the spontaneous emission of the two-level system. Because the system spontaneously emits from a high energy state to a low energy state, so not only the population change, but also the polarization of the system changes, and this as a whole results into this 2T dephasing rate, 1 over 2T dephasing rate. Yeah. So any spontaneous emission process is a dephasing process in itself.
So by putting it in a cavity, you are trying to minimize spontaneous dephasing due to spontaneous emission.
The thing about spontaneous emission is the spontaneous emission rate is increased, but the phase is between the consecutively emitted photon is not changed. The phase between the consecutively emitted photon is changed only by pure dephasing, because there's a kind of random process which depends on the phonon bath around it, and the phase is lost in the phonon bath which you cannot recover. And that's the only thing which is makes the difference at the end. So the faster you make the emission process, the relative phase doesn't change, only the emission rate change, but the relative phase only changes when the pure dephasing acts on the two-level system, and the relative photon phase changes, so they are no longer the same. Okay, so the normally used system, normally used excitation mechanism is an above band excitation, where the excitons where a laser which is above the band gap of the barrier layer is used to excite the electron hole pair into the surrounding barrier, and once they're excited into the surrounding barrier of the quantum dot, they relax into the quantum dot by different relaxation mechanism, and they emit finally by the ground from the ground state. The problem with such a scheme is that because one produces a lot of charge carriers, so there's spectral diffusion in the system because of the electrostatic interaction. Also, these relaxation processes, they insert a kind of a time jittering in the emission process. So the emission process, because they are mediated by phonon processes, so the emission time is not the same for each photon, and at the end, if you have to interfere them at the beam splitter, they will not arrive at the same time and destroy the Honko-Mandel effect. So what one can do better is to excite directly into one of these excited electronic ground shells, electronic shells. In this case, what happens that, of course, the spectral diffusion decreases, and also the time jittering increases because all these non-resonant processes are decreased. But the best one can do, or the ultimate process which one can do, is to do directly S-shell excitation, which means excite directly into the ground shell and emit immediate, and the emission is also done from the ground shell. So there are no non-resonant dephasing processes, and this is the most the process which can achieve highest photon visibilities or highest photon indistinguishabilities. And it has already been shown that, that under such excitation condition, the photon visibility as high as 90% has been achieved.
But does
Yes.
this work only for direct band gap materials?
Yes, yeah. This is only for direct band gap material, because when you have indirect band gap material, of course, you cannot avoid the phonon processes. So, yeah. So this is an indium arsenide, gallium arsenide system, so which is a direct system. Okay. So just one thing I want to note here is like a large challenge in such a solid state system is because the laser and the emission are exactly the same frequency. So the question is how to separate this. These two. So there are different techniques which are developed to separate the two. For example, this technique, the sample we use is as a special sample in which the quantum dots are embedded between two distributed Bragg reflectors, so that the Bragg it acts as a waveguide for the excitation laser. So that when the laser is excited from the side, it kind of acts as a waveguide. And because of the Fabry-Perot resonance, the emission is vertical to the structure, so one can directionally separate the excitation laser and the emission of the quantum dot. So the resulting setup is something like this. So it's an orthogonal excitation and detection geometry, and further we use this pinhole assembly and polarization suppression to get rid of the extra laser collection which we have at the end. And so the emission is finally studied by a monochromator or a spectrometer setup, and because the resonance fluorescence emission, it needs higher resolution to spectrally resolve the spectrum. We use a high resolution PL setup. High resolution PL setup, which is based on a scanning Fabry-Perot interferometer, which can achieve resolution as low as like 200 megahertz or so. So this was about the setup. So now I would come to the resonant excitation of a single quantum dot. So any two-level system which is resonantly excited with a laser can be, for example, a two-level system. If it is sufficiently strongly pumped, then one can say it's kind of a coupled system. So you have a coupled system for two-level system with a laser, such that the laser states are given by the number of Fock state or the number of photon state in of the laser photon at the position of the quantum dot. So the combined system can be then interpreted as a combination of both the two-level system and the laser photons. And if one introduces the coupling between the two systems, then the splitting appears between the two, which is given by the total Rabi's frequency. And the Rabi frequency is both a function of a Beer-Rabi frequency, which is a measure of power, plus detuning between the two. So at the end, one have a dress states formed, which are a linear superposition of the uncoupled combined states. And so what we study at the end is the emission from these dress states when we resonantly excited a single quantum dot as a two-level system.
How are these related to dark states? Dress states are different from dark states which one uses in CPT population trapping experiments.
Yes, but here, like in the context of the quantum dot, we have like bright state and dark state. So we excite directly into the bright state. So the splitting of this dressing occurs only for the bright state, and the dark state remains undressed. Yes. So one thing I would like to show here is that because all these different manifolds of this ladder are equidistant in energy, so one can combine this ladder into 4 levels at the end. So the effect of strong resonant excitation is that the two-level system is dressed into a 4-level system, so-called 4-level system, from which only 4 different kind of transitions are possible, as shown here. So there are 2 transitions which results into a kind of a triplet structure called it molar triplet. So the Rayleigh line is a combination, because these 2 photons are degenerate, they result into a stronger line, and there are side bands which are a result of these external outer transitions, which give rise to a 3-photon side band and an F-photon side band. So we have a central peak and 2 side bands, which is a signature of strong resonance fluorescence. Yes.
How strong is the coupling for this to make sense?
Sorry.
How strong is the coupling?
The coupling should be stronger than the radiative lifetime to see it. That's the limit one has, and normally that is achieved close to the saturation of the quantum emitter.
And do you care about the number of photons in your laser, or that's sort of?
That's not a problem because it's a degenerate. As I said, that this is equidistance ladder, so it doesn't depend on what your n is basically, because at the end. You come to this picture, which is a combination of all those ends, all these different.
It would make sense even if you had a billion photons or just 1 or 3 photons. This would still make sense, this picture.
What does photon does is, like, if you pump it with more photons, what it does is it increases the Rabi frequency, of course. And when you increase the Rabi frequency, the splitting increases. That's the effect. But in a more intuitive way, the number of photons doesn't make sense in this other way here. The effect of more photon is more stronger coupling and more strong omega. Yes. Okay, so how do we know when we have resonance fluorescence? So what we do is we scan the laser or the quantum dot resonance, And when we scan the laser over the quantum dot resonance, we see that immediately at resonance the signal increases. And when the signal increases, we know that this is the onset of resonance fluorescence from the two-level system. And if one draws the intensity of this line as a function of detuning, one gets such a profile, which is the absorption profile of the two-level system. And it depends highly on the excitation power. Like the higher the power, the broader it is.
Is this interpolation, does it take into account some kind of a shoulder?
Sorry?
This interpolation.
Yes. It's just a Lorentzian fit.
Yeah, but you were trying to improve that shoulder in the early part.
No, we didn't. So it's kind of a noise in the, for example, if you scan, there is some small power fluctuation as well in the laser. So maybe it's because of that. But there's of course uncertainties in the experimental conditions. So if you scan over, maybe everything is not the same all the time. Yeah. So if we stay here on this resonance and measure the spectrum of with a high resolution PL, what we get is something like this, which is very close to what we should observe at the molar triplet. And the red line is a theoretical curve, theoretical fit to the data, and you can see that the rest is due to the excess laser signal, because of course you cannot completely get rid of the laser. So the rest is just, so what we achieve here is a very high signal to noise ratio and a resonant fluorescence from a solid state emitter, which is an achievement in itself. But so to further know that if it's really a resonance fluorescence emission and not some other thing, what we do, we increase the excitation power. So as I said, told earlier, that the more you increase the power, the Rabi frequency should increase. And as you can see here, the arrows show that the Rabi frequency, that the sideband move further from the Rayleigh line as the excitation energy is increased. And if one plots the Rabi frequency extracted from each plot as a function of square root of power, one get as a linear behavior, which is what is observed for expected for a true resonant fluorescence signal. So this is again confirmed that we have signature of resonant fluorescence in the system. Here I would like to comment that you see some extra peaks here. These extra peaks are the neighboring Fabry-Pérot modes, so we don't take them into account.
So what's the maximum temperature at which you will get these kind of results?
Oh, this is hard to say at the moment. I don't have any, but normally from what we have done, we have achieved resonance fluorescence until 30K or so. Yeah, but it's hard to say exactly how high temperature one can reach with it. Yeah, maybe mostly 70 or 80K, but that would be the limit normally in quantum dot system. Okay, so now I come to the main part of the setup after showing you of the talk, after showing resonant excitation of single quantum dot, is the photon statistical analysis on this emission. So what we want to do is we want to do photon correlation measurement on each of these different photon channel. And if you look at the width of this photon channel, they are on the order of 1 to 2 gigahertz. If you look at the separation between the sideband is the order of omega, which you can of course depend on power. In our case, it changes from 4 to 11 gigahertz or so. The resolution of our spectrometer is something about 7 to 8 gigahertz. So this is given by this green window. This is the resolution of a setup, which means that the resolution of a setup is not sufficient to resolve these different spectral components. And to resolve this component, you need to obey this relation, this inequality. So the right inequality is easily observed, but the left inequality is at the limit here. So what we need is some kind of an extra filtering mechanism to achieve this. And this we achieve by using a very simple method of Michelson interferometer. So what we do is we input the whole molar triplet into a Michelson setup, and for a certain delay, one can achieve conditions for certain difference between the spectral difference between the lines, is that both the sidebands, for example, at this delay, both the sideband interfere constructively at one output, but destructively at that output, and the other way around. So what you can get at the end is at the what output you get both the sideband, and the other output you get only the central peak. So you can separate the central peak from the And this is the results shown here. So this is the case where the central peak is minimized, so it's almost gone, and this is the case where the side peak is minimized. So you can use this technique as an extra tool in addition to the spectrometer to select your signal. So just a brief introduction to what we want to do is kind of photon statistic measurement we want to do, and how it works. It works like the photon signal, it is split on a beam splitter and fed into an avalanche photodiodes, and depending on the start and stop signal where the photon are detected, the correlations are measured, which is given by the second order photon correlation measurement, and depending on how the behavior of this function is close to a delay between the two, start and stop, it determines what kind of a light source you have. For example, if you have a thermal source, then the correlation, light comes in bunches, and when they come in bunches, both the detector clicks simultaneously at 0 delay, and that's why thermal light shows high G2 value at 0 delay. But what if you have a single photon emitter? If a single photon emitter, you would never observe 2 clicks at the same time, because it emits single photon, and that's why for a Fock state where the number of photon is 1, the correlation should be ideally 0. And for a coherent state which is in between, mainly for a laser, you get a Poissonian, which is an uncorrelated light in photon statistics. So there are certain values which are important, for example here. So for a single photon source, it is important to have a G2 value of 0 below 0.5 to be a single photon source. For a cascaded photon source, which means a photon which comes in pair, it needs to be more than 2 to be sure that it is really a cascaded photon source and not thermal light or so. So these are the 2 important parameters which are needed to be.
Is 0.5 just a conventional value?
Yeah, it's just it's a convenient kind of a reference one used for a single quantum emitter. So if it's below 0.5, you're more confident that it's a single quantum emitter. Yeah. So in the first part of the measurement, what I would show is like what we did was we select only the central component of the monotriplet. This is now on a we increase the Rabi frequency so that we can see it also on the spectrometer. So this is how this image looks like, and we select only the central component, minimize both the side component, which is not shown here, and do photon correlation measurement on only the Rayleigh peak. So what we expect for this case, we expect a Poissonian statistic for this case, which means that the correlation should be 1 for all the time delay. Why we should expect this and why we should not expect an anti-bunching because it's a single quantum emitter is the reason because when a Rayleigh photon is emitted, the system ends up into another rest state from where another Rayleigh photon can be emitted, and because we have a relatively small, we have a time resolution. Because of the time resolution, you cannot see the anti-bunching, or which is called the signature of single quantum emitter, and that's why it should show Poissonian distribution, photon distribution. But instead what we observe is some kind of a bunching here, which is on a much longer time scale than the lifetime. This bunching, if there is due to the system, should be on the order of the lifetime, but this is something else which is here, and in a quantum dot system, normally this is due to the dark states. For example, we excite resonantly only the bright state, but the system can also jump to a dark state, and when the system jumps to a dark state, it becomes dark for some time, and there's a switching back and forth between the dark state and bright state on a longer time scale, and when that phenomenon occurs, so on top of this Poissonian correlation, you have an extra correlation which is given by this switching time. So the 32 nanoseconds mean that the switching between dark and bright state is on the order of 32 nanoseconds. So this kind of an effect is called as blinking effect, and this is not due to the intrinsic two-level system behavior. Okay. So in the next stage of the experiment, what we did, we minimized the Rayleigh peak, so you only see the side peaks of the 3 monotriplets. And so what we do is select only one of the spectral component here, or only one of the side band, and do photon correlation measurement on that. And what we observe is something like this. So again, we see this kind of a long-term exponential, which is due to the blinking, because blinking is all the time there; it cannot be avoided. But what we see additionally here is a very strong anti-bunching, or single photon character, which means that each of these sideband acts as single photon channel. And why does it do that? Is because of this. So if a T photon is emitted, for example, this is the system ends up in address state 2, and from this address state 2 another T photon cannot be emitted. So an F photon has to be emitted so that the system is prepared again to be able to emit another T photon. So there's always some time between two T photon emission, which is on the order of the lifetime. Given here, this fit is of the order of the lifetime of the quantum dot. So what I show here is that the single photon channel from resonant fluorescence, they can show clear photon anti-bunching, which means they show clear single photon character, and we get very high count rate, about on the order of 6 megahertz from these. So these are they are spectrally narrow single photon channels which one obtain from resonant fluorescence of single quantum dot. Yes?
Have you done cross correlation between the T and the F photons too?
Yeah, that comes next. Yeah. Okay, so this was what happens when we detune the laser. What happens to the system when we detune the laser? So this is the spectral series of the resonance fluorescence shown as a function of laser detuning. So what happens that the Rayleigh photon, which is at the center, it shifts with the laser as the laser is shifted on either side of resonance, and also the side peaks, they shift in energy as well. So what we expect theoretically, for a dress state, if the laser is detuned, we expect kind of anti-crossing between the two dress state, which is a signature of strong coupling between the laser and the two-level system. And if you plot the spectral position of these of the side peaks, what we see is a manifestation of this anti-crossing as a spectral position of the two side peaks. So what happens when you increase the detuning is that the effective Rabi frequency increases as the total Rabi frequency depends on the power and also on the detuning. So if you increase the detuning, the splitting between the two increases and the Rabi splitting is also increased, as given by this theoretical curve. So the question is, what is the effect on the population of these dress states on the detuning? What happens to the dress state population when you detune the laser? For example, this is, as I showed here, these are the coefficients, C and S are the coefficients of the dress state. So, and here you see the steady state population of dress state 2 and dress state 1. So, and here they are plotted, so the steady state population of the dress states are plotted here as a function of detuning. What happens if you strongly blue detune, if you strongly blue detune the laser, what happens is the system is mainly prepared in the state 1. So if the state 1 is mainly prepared, then what happens is the T photon would be emitted first, because you populate the system more, and the F photon would follow. But what happens if you red detune strongly, the system would be prepared mostly in the state 2, because the state 2 has more population, and the F photon would be emitted first and the T photon would follow. So what you can do is, just by detuning the laser from resonance, you can change the population of the system and the photon emission sequence of the sidebands. Okay, what do we theoretically expect from these scenarios? For example, if we take, as you said, if you take, for example, T as a start photon and F as a stop photon, and do a cross correlation, photon correlation between the two channels, what do we expect in this case? So these are the theoretically expected plots which we expect. So if you have strong blue detuning, for example, the case, then the T photon, which is the start, it gives a click at 0, and the F follows with a certain lifetime, which is given by the emission lifetime, given by, again, the lifetime and the coefficients. So what you see here is a highly asymmetric time asymmetric correlation peak, which means that there's a certain time ordering in the photon emission sequence, and that's why the photon correlation is asymmetric. And also the correlation strength is very high, which means that the photons are emitted in pairs. So they are not only prepared in time ordering, they are also prepared in pairs. And if you keep the start and stop at the same, the blue detuning the red detuning would have the completely opposite effect. Okay, so just as a first measurement, what we did, we sent both the side bands into the correlation measurement so that both can act as start and stop. And what we did, we changed the detuning and measured the correlation of the combined two sidebands. So at resonance, or close to resonance, there is no bunching. There's this large scale bunching which is due to the blinking effect, but this is no real two-level system effect. But as you detune on either side of the emission, immediately the bunching appears, which means that the cascade process starts as you detune from resonance. And this is shown here for two different powers. For example, for low Rabi frequencies, you see that immediately from detuning, the correlation at 0, which is given by the peak height at 0 delay, it immediately increases as you detune the power on either side, the detuning on either side. Here you can see that both the plots have different curvatures, so it means that it also depends on not only on the detuning but also on the power, on the bare Rabi frequency. So what if we plot it as a function of relative detuning, which is the detuning divided by the Rabi frequency? So we see that both collapse, and which means that this effect of cascade appearance is due to the relative detuning and not only due to detuning. So you need not only take into account the detuning but also the Rabi frequency. So here I showed that the cascade appears as you detune, and now we come to the measurement where we do this actual measurement in which we want to show the cascade, where we select T as a start photon and F as a stop photon. So we did this for red detuning condition, and what we see is like this. So what we said, what should observe is a sharp rise on this side and a fall with effective time scale on this side. But instead we see a slow rise which is close to the resolution of the setup. So we cannot see the sharp rise because we are resolution limited on this side. But here on the other side we see a fall of the signal, of the correlation signal, which is very close to the effective time scale which we theoretically expect for the signal. So here, and also the bunching is more than 2, which means that you have high probability of 2 photons coming out, and in addition there is time asymmetry in the signal, which means that it's really a cascaded photon emission in this case. And we did the same for blue detune case, where we blue detune the laser, and we observe something like this. So we don't observe a sharp rise, but rather a rise with respect corresponding to the resolution of the setup, and a fall which corresponds to the effective lifetime. And so what I have demonstrated here is a 2-photon cascaded emission for mono sideband. So these sideband can not only be used as a single photon source, but they can also be used as a cascaded photon source, and you can even control the emission sequence of these sideband photon as well. So I think I will stop with this because I have other part of this talk, but time is not enough, so I will thank for your attention. Yeah.
We can have
It's more, so I didn't thought that there would be question in between, so
I think we can have 5 more minutes for the talk, or we can have 15 minutes in questions, and later. I think we can have 5
more
to 10 more minutes for the talk, and we can stop at 3 with the question answer.
Okay, good. Yeah, okay. So
you can talk about dephasing.
yes, okay, I will. Yeah. So yes, okay, I will try to make it as quick as possible. So this was about photon emission statistics in resonance fluorescence. Now what about the dephasing in the system? How does it work? For example, for an ideal case, what atom optics suggests is that the dephasing, which is basically, this is the spectral function of a model triplet, it is given ideally by only the lifetime. And the power should, so these are the side widths which we should Fourier transform, we should observe in a Fourier transform limit, and this situation should not change with increasing excitation power for an ideal 2-level system. So the width should not have the excitation power should not have an effect on the width of the sideband. It should only have an effect on the Rabi splitting. But what happens if there's a 2-level system which is coupled to a phonon bath? And it is strongly coupled to a phonon bath in the indium arsenide, gallium arsenide system. So what happens is that there's not only energy renormalizations, which means that this model is no more valid because the emission and absorption rates are changed. So what happens is that the radiative rate, it is enhanced by extra phonon dephasing rates. So the radiative dephasing is not only given by 1 over T2 T1, but some extra term which depends on phonon processes. And these phonon processes either increase the emission rate or either increase the excitation rate. So it's no more valid, and the resulting expression is something like this. So what we tried to do is, like we did this power series that I showed earlier, and we tried to use the same theory here to fit this, and we get a very nice fit of the data here. And here what we see is, it's not shown here, it's shown in the next slide, that the full width half maximum of this sideband increases with the excitation power. So this is not what you expect from atomic system, this is something extra, and this is most probably due to the solid state matrix or the phonon in the system. So these are the time resolved these are the time domain measurement which we did using Michelson interferometer. So you can not only measure resonance fluorescence in the spectral domain, but you can also do it in the time domain, and you see this kind of oscillation, which is the beating of these three frequencies in the time domain, which is fitted again with this phonon dependent model. And this is the result of this fitting, and here is the dephasing of the total sideband. I would skip this one. So here, this gives the black line are the result of the spectral measurement, and the blue line are the result of the time domain measurement. And as you can see here, that the dephasing increasing with excitation power, so which means that we have excitation induced dephasing in the system, which is not in an atomic system. So the dephasing of the system really depend on the excitation as well. And just as a final thing, I would show that here we also analyze the dephasing of the system as a function of laser detuning, and as you can see here, the dephasing also change with detuning, which is not theoretically explained until now. So there is no theoretical explanation for it now. But solid state emitter systems, they are not as simple as a as atomic level system, because they have these higher complexities of phonon in the system, and because of these phonon, there are these excitation induced and detuning induced dephasing. So with this, maybe I would like to finish. I have a third part, but maybe for next time. Thank you for your attention.
Questions?
Yeah, I have a question.
Yes.
I'm still not sure what kind of material do you use for making carbon dioxide? Some sort of semiconductor material?
Yes, so we use indium arsenide, gallium arsenide system. So gallium arsenide is the barrier, which is the surrounding material. So gallium arsenide has a large band gap, and indium arsenide we use as a quantum dot material, which has a smaller band gap.
And what is the physical size of the system?
The physical size, it's a kind of a lens-shaped structure. So the height normally is from 3 to 4 nanometer, and the size, the lateral dimension from 20 to 40 nanometers. Yeah, and these are grown by MBEs. Also MBE and molecular organic vapor phase epitaxy as well. MOCVD kind of technique.
Your reagents are not from the single dot.
Yes, yeah. So all these measurements were shown on single dot because they show anti-bunching character, and that's a real character of a single quantum emitter.
How do you get the emission from the single dot?
From the single dot. So what we use is a kind of a microphotoluminescence spectroscopy in which we focus a laser spot via an objective microscope on a spot size of like 2 micron diameter, and because the dot density is very small, very low, so on the average we have maybe excite 1 dot in such a small area, although there are many dots on the sample. So the thing what we do is we focus the laser beam.
So you have a kind of a filter like size of microns, assuming that there are few number of dots lying randomly.
No, we don't have any kind of filter. Actually, this is a bit different experiment because we excite from the side, so we excite many dots. But what you do is you just center or maximize on the emission of one single line, and if you do a photon correlation measurement on this and see a clear anti-bunching or single photon character, then you know this is a single quantum emitter. Yeah, so maybe you can obtain more lines, but under resonant excitation, because each quantum dot has a characteristic spectral, but they are a characteristic emission energy, so you can only select one at one time, not many. Under non-resonant excitation, of course, you collect many because you excite all the charges in the barrier and they can relax into many dots at the same time. But under resonant excitation, because each shells of each quantum dot has a characteristic energy, that's why you spectrally select only one quantum dot. Or excite only one quantum dot. Yeah.
I'm still not sure how do you control the direction of emission. So your excitation is like this and the emission is like this.
Because you have a dBr structure. In a dBr structure, the Fabry-Perot resonance mode is mainly in this direction. Yes. Right. So the emission is mainly in this direction from the quantum dot, perpendicular to the dBr structure.
Okay.
You have kind of two mirrors basically.
Right. That's true. But the quantum dot itself, how do you? So you are saying that the emission is taking place only in that direction?
No. It's in a 4 pi direction, but in that direction is
that side is the
enhanced.
One that has that.
It's even more controlled in a micropillar cavity, for example. If you embed it in a micropillar cavity, it has a certain directional geometry, and also the photon density of state in a cavity changes drastically, so it will preferentially emit in vertical direction then. Yeah.
So does some of this work have direct applications in photon microscopy or fluorescence microscopy in biological samples? Are there any direct applications of this kind?
I exactly don't know, like maybe there are, but for example, if such a narrow band single photon source can have many applications. For example, there are many works in atom optics which study interaction of such a Fock state light or really well-defined light with single quantum emitter. So single quanta interaction, those kind of interaction are really interesting phenomena. So they are already being studied in, for example, single photons from molecules. So one molecule emits single photon, another detects it, and there are really basic physics inside. Yeah. So
have you tried to introduce spin into your molocryptids to get spin molocryptids?
It has already been done by another group. So they did some spin. So what they did is like they applied a magnetic field so that they shift they split the two-level system, and they get a splitting of the side bands as well as a result. So this is already, which you can take, like which belongs to which spin, up spin or down spin. Yeah.
Because in one of your initial slides you had an additional shifting of energy levels because of the lattice symmetry.
Yes.
So you break the symmetry in your sample.
Yes.
Impurities or
due to the shape. The shape is very asymmetric, so it's only for the D2D symmetry. But here normally it's a C2V symmetry, not a D2D symmetry. Yeah.
I have one more question.
Yes.
It's related to the plot that you've shown where you expect a Poisson distribution.
Yes.
So my probability theory is kind of rusty now. You had this plot of time period, right?
Yes.
And you were saying that you expect a Poisson distribution.
Yes.
Why do you expect a Poisson distribution?
From the Rayleigh line.
But
From the central peak.
No. My question is this: Poisson distribution is for discrete random variables, discrete quantities. Time delay is continuous. Why would you expect Poisson distribution for continuous random variable?
You mean for laser even?
No, I'm talking general statistics.
Yeah, general photon statistic.
Any statistic, doesn't matter. It's probability.
Because okay, I don't know how to explain it, but in terms of
but this is true, right? The Poisson distribution is a random distribution.
Yes, it's a random distribution. So yes.
So time delay is a continuous variable. Why would you expect that?
You mean in terms of variable? But it's kind of like the time delay is only a measure of, it's not what you measure. What you measure is how many photons you have, the statistics.
So your numbers.
It's a kind of domain in which you measure. It's not what you measure. Yeah.
And he has been showing the correlation functions he hasn't showed the distribution functions, but he's been showing, I think, is the correlation function, the G2 tau as a function of tau, and tau is he's doing these coincidence measurements, in which tau is variable. If you have a start and a stop signal, and you measure the time delay between two
Incidents.
photons and looking at how they are correlated. So he's been showing the correlation functions.
Even that plot with the time delay in the x-axis was correlated.
It was a
All of these are correlation. Right?
G2 second order.
No photon distribution function. Yeah.
But you do expect Poisson distribution for coherent light.
For counting.
For counting, for coherent light,
Right.
purely coherent light.
Exactly. So counting I agree, but the plot was okay. I didn't pay attention much.
So he has these single photon counters that are actually counting the photons.
Right. So that's fine.
Yeah.
Just one. Okay. So again, coming back to that Fabry-Perot, so you would need to have the emission wavelength to be a certain wavelength that corresponds to the modes of that Fabry.
Yeah, it's very broad mode normally. It's like 2 to 3 nanometer broad, and the emission is like really narrow. And it is, it's like what some 1 gigahertz or 2 gigahertz. So
Okay.
yeah,
But
it's within this broad Fabry-Perot resonance.
okay.
Yeah.
If there are no more questions, let's thank the speaker once again.